And I'm sure if it was left there, it wasn't left there as any kind of a deceptive tactic, but there are far more series than just geometric and arithmetic. There are a lot more series, and we're going to explore some more of those here today, and some tests to be able to deal with them. So what are the two tests that we have learned so far? GST, the geometric series test, and the nth term test. So tell me about the nth term test. What can the nth term test do? It can really only do one thing. Yeah, it'll tell you the series diverges, but it will not tell you anything about a series that converges. Okay? What is the geometric series test? Can it go both ways? Can it tell you converging or diverging? Yeah, it'll tell you both sides, right? It'll tell you one way or the other. And then the cool thing about geometric series is that you can actually find the sum pretty easily. You can find exactly what the number sum to be. We're about to go to a place where we're going to be looking at series where we can judge convergence or divergence pretty, relatively easily. But to actually find the sum can become very difficult, right? Sometimes with these types of series, maybe there are formulas that could be used to find the sum of the series. Those formulas were the result of maybe someone working on their PhD trying to prove, like that was the whole focus of their PhD, was to prove that this series sums to this and developing a formula for that type of series. So not trivial, right? Not trivial at all. We're talking about someone who has taken, 7, 8, 9, 10 years of post-high school math trying to prove that something actually, exists, and here's what it would be. So pretty difficult stuff. So we're going to take a look at a couple of other tests here this morning. While I'm doing that, just a reminder for you guys, we've got our 9.2 to 9.3 quiz coming up next week. It's 2:15, so that would be Wednesday, wouldn't it? Okay, so we're gonna poke our way through to 9.3 quite a bit today. We may finish it, may not finish it. We'll definitely finish it on Monday. That'll give us a few extra days there as we kind of work our way towards that 9.2 to 9.3 quiz. All right, so the first test we're going to look at is the integral test. The integral test, as you might guess, involves an integral, and this will actually feel like an old thing that we've done. And so let's focus on it, and we'll go back and look at the conditions for it. So this is the integral test right here. This represents our series right here, sigma from say 1 to infinity of a sub n, where a sub n is that nth term. This is something similar to that, right? This is the integral from 1 to infinity of f of x. This is all predicated on a sub n equaling f of n. So the function that you would be anti-differentiating and doing a definite integral of is equal to that nth term. So in other words, if you have a series and you want to test it out, you can take the nth term and just do a definite integral from 1 to infinity of that nth term, and then based on the result of that, we can make a judgment. So the stipulations are this, and I think these conditions are going to be pretty important this year. So for the integral test to even work, f has to be positive, right? So the nth term can only produce positive terms, and all the stuff in between has to be positive as well. F has to also be continuous. And then this is also an interesting one, decreasing, like exclusively decreasing for the interval, bigger than or equal to 1. Okay, so positive, continuous, and decreasing. Maybe we can look at why that is. I think there's a couple things that are pretty obvious and maybe some other things that are not as obvious. So if f is positive, continuous, and decreasing, and a sub n equals f of n, then we can calculate this integral here, and here's where we can make our judgment. Either the series and the integral converge, or they both diverge, but if they converge, it's not necessarily going to be to the same value. So let me give you for instance. Let's say that we do this integral right here. Let's say that we calculate the integral, and let's say we get, ln of 7 or something like that. So that's a real number, right? ln of 7 is something that can be put on the real number line. So that's an actual real number, and so that means that integral converges, which means that the series converges too. But it doesn't mean that the series has a sum of ln of 7. All we can really do here is make a judgment that the series converges or diverges. So if we were to do the same sort of test, and instead of ln of 7 we get a diverging answer for that integral, then we can say that the series also diverges. Okay, so they're going to go the same way. They're either going to both converge or both diverge. We'll do some examples in a second. Okay, and let's see here. The positive, continuous, and decreasing concept. Let's talk about that just a little bit here. If I were to draw a graph, let's say that f of n. Let's just follow the conditions here. Let's say it does something like that. Positive, because it's above the x-axis. Continuous, I suppose for obvious reasons based on the graph there. And decreasing, again, based on the graph. Let's talk about why that is so important. Why that is so important. So when you think about how the relationship of a sub n and f of n work, what you're going to essentially be creating is, like if you have these various terms, like term number 1, term number 2, term number 3, dot, 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 essentially what you're creating is a right sum of these various terms, so on and so forth. So here's how this actually works. If f of n is decreasing, like it's supposed to be, if f of n is decreasing, then if you think about the area under the curve, wouldn't the area under the curve of the function always be a little bit bigger than the sum of the rectangles? So if you think this through, if the area under the curve is always a little bit bigger than the sum of the rectangles, and the area under the curve converges, with the rectangles always being a little bit less, wouldn't the rectangles have to also converge? That's kind of the logic behind positive, decreasing, and continuous. Okay, so as long as f of n is positive, continuous, and decreasing, then at each point in there, at each time that you calculate, bless you, a value for each term, you're going to get something, like over that interval, something a little bit less than the area under the curve. So that means if the area under the curve converges, then absolutely the little rectangles would converge as well. Okay? Does that make sense? Okay. Let's leave it at that for the moment. We can explore a little bit more with that. None of you asked any questions, so I thought I would just bring that up. Okay, so then let's look at the other one here. The P-series is something that we have looked at in the past. You guys remember this from when we did the improper integral chapter? P-test? P-test? Okay, so a P-series is any form of this right here, or the sigma from 1 to infinity of 1 over n to the p, where p is some power, right? Like to the second, to the third, to the 1/2, to the whatever. So p stands for power, right? That's why they use the letter p here. And so I'm trying to remember here what comes next in your notes. If you remember back, maybe does this show up on the next page? Does the p-test actually show up? I can't remember. Yeah, it does. Okay. And then a new series is what we call a harmonic series. A harmonic series is something that will likely show up a lot in the future. So don't think of this as just a little footnote. A harmonic series is just a form of the p-series when p equals 1. So this would be like sigma from 1 to infinity of 1 over n, and it would look something like 1 plus 1/2 plus 1/3 plus 1/4, so on and so forth. A general form would be sigma of 1 over an plus b, where a and b are both constants. I think the harmonic series is pretty interesting because this is the one example of a series that the nth term test kind of fails us. Can I give you an example? Let's say we're doing a really basic harmonic series. Let's say it is just the sigma from n equals 1 to infinity of 1 over n. And let's say we're trying to determine the convergence or divergence of that. Your first thought maybe would be the nth term test, right? So we'd say limit as n goes to infinity of 1 over n. And what would that equal? 0. Yeah, so you could say, hey, you know what? The nth term is headed to 0, and here's where you'd be tempted to say something wrong. The nth term is headed towards 0, therefore the series must converge. And that's false. That's false for a number of reasons, one of which is the p-series test. But you could also prove that using the integral test, and I think we'll get a chance to use that here in just a second. Okay, so 2 tests. We'll talk about the p-test, I think, here in just a moment, but let's practice it here. The p-series test is right here. If you have a p-series, then if p is bigger than 1, then the series converges. It's a pretty quick judgment. If p is between 0 and 1, then including one, then the series diverges. Why don't we include negative p-values here? Why do we not even consider?
It's already in the bottom.
It wouldn't be in the bottom anymore, right?
Yeah.
Like if it was 1 over, n to the negative fourth, isn't that really just n to the fourth? And why would we even bother analyzing that? Isn't that just a clear, think about it. If you had sigma from 1 to infinity of 1 over n to the negative fourth, that would just be n to the fourth, right? And as n goes to infinity, what is n to the fourth doing? Yeah. Is your silence like, yes, I get it, silence? Okay. So, sorry, I'm in a fog. You're going to have to respond with like, yes, Mr. Anderson, I get it. Or no, I don't. Please respond. I'm not trying to insult your intelligence. Are you with me? I hope you are. I'm just going to proceed as if you are. You feel free to stop me if I am incorrect. Okay, so let's do number one. So number one, we're supposed to just determine the convergence or divergence. Please understand, nowhere in here am I saying what is the sum. I'm not asking you, what does this add up to be? I'm simply asking you, if you did, would you get a real number or would you get infinity? That's really all we're asking here. So take a look at number one. It says sigma from 1 to infinity of n over n squared plus 1. And it doesn't really give you any direction as to what to use. So I think we should probably use the nth term test first. At least do it mentally. Because if the nth term test is going to tell you something, it'll tell it to you really quick, and you'll be done. So what does the nth term test tell you here if you do limit as n goes to infinity of n over n squared plus 1? I'm going to go ahead and wait for an answer. It's 0, Will. Thank you. Okay. Please don't make me assume that you're getting this. Please don't make me assume all the way up until your quiz and be like, oh crap, they didn't get that.
Why would it be 0?
Oh, thank you for asking, Allie. This interaction is warming my heart. I love it. Okay. So limit as n goes, so I'm going all the way back to the nth term test. So this is from a couple days ago, but it still applies potentially. So if I do limit as n goes to infinity of n over n squared plus 1, I suppose you could do this in a number of ways, but to me the easiest way is to compare the degrees, right? Whenever you're doing limit as n goes to infinity, if the degree in the top is less than the degree of the bottom, then that old pre-calc rule tells you that you'll have a horizontal asymptote at 0. So this is a really old thing. Not that it's an easy thing, but it's really, really old. And so it still applies, though. It still applies. Here's another way. You can take the degree of the denominator, and you can divide every single term in the top and the bottom by that n to that degree. So you could go n over n squared over n squared over n squared plus 1 over n squared. And so that would give you, I'm going to erase all this here in a second. Limit as n goes to infinity of 1 over n over 1 plus 1 over n squared. And so then as you apply infinity, that limit as n goes to infinity, well, 1 over n would be going to 0. And the denominator would be 1 plus 0. So you get 0 over 1, so you still get 0. So that's another example of reasoning you could use. But I think whatever reasoning you do use, you're going to get 0 there. Now here's the key thing. This is called the nth term test. And this applies, honestly, this will apply to pretty much every series we look at from here till the end. Sometimes it's going to tell us something, sometimes it won't. What does it tell us here? Say again? It doesn't diverge. At least we don't think so, right? Not yet. So we can't say for sure that it doesn't diverge. We can definitely say, though, that the nth term goes to 0, right? So it's not going to obviously diverge at this point. It still could diverge, but it would be for a different reason. So in other words, the nth term tells us nothing. Nothing. It just says, keep going. Find a different test. Does that make sense? It says, you know what, you haven't reached a conclusion yet. You're going to have to use a different test. So does that make sense to you guys? Remember, the nth term test is a really negative thing. It's only going to tell you, yes, this series diverges, stop, or I'm not going to tell you anything. Find something else. find something else. Okay, so the nth term test here, I think is always worth considering. I do. But I think you probably want to do that more mentally than anything else because it'll occur that, it'll happen where it actually does help you from time to time, but in a lot of cases it simply won't. So this is one place where it didn't tell you anything else. Okay, so the next thought would be, okay, so nth term test didn't tell me what I wanted to know. What are some other series tests that I do know? I do know the geometric series test, right? But the geometric series test only works on geometric series. Is this a geometric series?
No,
Why?
because in a geometric series, it's r to the n, and n is a base, not an exponent.
Well said. The n has to be an exponent for it to be geometric. She said it extremely well. Do you get it? Okay, so it's not geometric, so you can't use the geometric series on something that's not a geometric series, right? They got to match up. So if it's not the geometric series and the nth term test didn't tell us anything else, why would I put this in the notes at this point? Maybe the integral test works, or maybe the p-series test works, right? So is this of the two, the p-test is easier, right? Because the p-test, you simply look at the exponents and make a judgment. So is this a p-test? This is a p-series, based on what you've seen. I know you don't have a lot of experience, but is this a p-series? And of course, a harmonic is just a specific type of p-series. So that's sort of, I don't think I would differentiate between the two at this point. So you guys think it's a p-series or not? There's one thing that makes it not. Say again? Well, so the 1 I think is okay, right? Because to go to Grace's point, 1 over an plus b is a harmonic series. That's a generic form of a harmonic series. And so the b could be a 1, right? The b could be a 1, sort of, kind of. I think there's something else that, there's two things. Yeah, go ahead. The n in the top really turns it into not a p-series. For it to be a p-series, it has to be a 1 or easily turned into a 1. Like if it was a 7, you could just factor the 7 out, right? So it really has to be a 1 there. So what I'm trying to help you build is like a logical progress of attack on these things, right? Logical progression of if it's not this, then it's this. Oh, it's not that. Well, maybe it's this. Oh, so then it must be this, right? It's a logical framework of thinking about this. So nth term test told us nothing. It's not a geometric series test for the reason that Grace said. It's not a harmonic series because of the n in the top. It's not a p-series because of the n in the top. It's not a harmonic series because of the squared anyways. So the only other alternative we have at this point is an integral test. Does that make sense? So here's how we set up the integral test. We're going to make this our nth term. We're going to make that our integrand. Here's how it would go. I would say integral from 1 to infinity of n over n squared plus 1 dn. So I'm simply going to take that nth term and make it my integrand. And now we're going to try to work with this integral and see what happens. Good? Okay. So whenever one of your limits is infinity or there's an infinite discontinuity, we have a name for these integrals. And what is that name? Improper. And what always goes with an improper integral? Limits. Yeah. So I'm going to go limit as b goes to infinity of the integral from 1 to b of n over n squared plus 1 dn. Okay. By any chance, do you guys recognize that integrand? Yes? Yes. Very good, but it's off by a factor of 2. Good. Okay, so it's going to be limit as b goes to infinity, and it's going to be 1/2 ln of, I don't really need to worry too much about the absolute values here because of what that input is and the fact that we're only going to go from 1 to b and b is heading towards infinity. Okay, so now we use FTC1, right? Hopefully this is a good review of some chapter 8 stuff. So it's going to be limit as b goes to infinity, and it would be 1/2 ln of b squared plus 1 minus 1/2 ln of, I guess it would just be 2, wouldn't it? So what do you think?
I think it diverges.
Why?
Because if you do 1/2 when the natural log of e squared plus 1, you're going to be like 1/2 the natural log of infinity. So infinity squared plus 1 is infinity, which is infinity. So it diverges.
Yeah, ln continues to increase, right? As b gets huge, ln, I mean, it slows its rate of increase, but it continues to increase. So as b goes to infinity, it makes the input go towards infinity, which makes ln of that also go to infinity. So, if you wanted to be cutesy with it, you could say it's infinity minus 1/2 ln of 2. And what chance does 1/2 ln of 2 have of slowing down infinity? None. Okay, so here's your logic that we'd use here. I'm going to reinforce those conditions. We didn't really focus on this. Maybe we should have. We could use a calculator to focus on this. But I'm going to say this. Because n over n squared plus 1 is, remember those conditions? Positive, continuous, and decreasing on the interval from 1 to infinity. Those are all three of those things are the conditions.
Do you have to prove those?
No, I think you're going to have to just recognize that that's what they are, and once you're at least able to mentally acknowledge that that applies, you could use a calculator to certainly see that, then I think we can just proceed. But let's remember that that's what the conditionings are. And the integral from 1 to infinity of n over n squared plus 1 diverges, then sigma from 1 to infinity of the same thing also diverges. And then you don't really have to put this on the AP test. I just want to see it for the moment here, that you're showing that you're using the integral test. So I just put integral test there at the end. Okay, so we met all the conditions. N over n squared plus 1 is positive, continuous, and decreasing on that interval. We found that the integral actually diverges, therefore the series will also diverge due to the integral test. Question, Grace?
Every time we use the interval test in our explanation, do we have to say because it's positive, continuous, and decreasing?
So, yeah, that's a good question. I do want to make sure that you understand that this year the AP test is a little bit different, right? And they're trying to put an emphasis on like notational fluency. Like, are you communicating clearly? So I think they might be a little bit less forgiving for like unclear notation. And also, they've always done this with certain things, but they're putting a renewed emphasis on understanding the conditions for certain theorems and procedures to be true. And so I'm going to do it in class. I'm not really going to expect that you write all that out on a test like with what you just referenced there, the positive, continuous, and decreasing on the whatever the interval happens to be. But I'm going to do it in class a lot so that just in case in the future you get asked a question that might bring those conditions into play, you'll maybe remember, oh yeah, positive, continuous, and decreasing. Those are the requirements for the integral test.
But on your test, if we do it in
Yeah, not unless it addresses that, right? If the question addresses some form of those conditions, obviously then you have to. But in your explanation, I don't think so. Yeah. Okay. Anybody else with a question? Okay. So let's take a look here at our next one, number 2. There's a variety of ways you could handle this, depending on how good you are at recognizing things. So I hope that I can get you to that place where you'll recognize things really well and make this easy on yourself. So let's start off with this. I'm going to just try to keep hammering this way of thinking in your mind. Later on, there's a little flow chart that will help you with this. But for the moment, I want you to look at number 2. And I want you to think, all right, what does the nth term test say about number 2? The limit is n goes to infinity of 1 over n. Say again? Well, but we don't know that though, Jared. You keep saying that it doesn't diverge It doesn't say that. It doesn't. Here, like, so if we write it out real quick, limit as n goes to infinity of 1 over n, what is the answer to that? 0, yeah. Okay, so just because we get a 0 there, we can't say it doesn't diverge. Say again? You could say that the end behavior approaches 0. I agree with you there. But you cannot say that we've proven a lack of divergence. Because there's no gray area. This is very binary. Either this series diverges or it converges, right? There's no, it almost did or almost didn't. So for us to say it doesn't diverge at this point, what does that imply? It has to converge, right? So I don't think we can really say that, Jared, that it doesn't diverge. What can we say? Like, what does the nth term test tell us? Nothing. It's silent, right? So the 0 stands for the decibel level of its proclamation. Nothing. That makes sense? So the nth term test tells us absolutely nothing here. Now, if we got this, it would have to be something other than that, but if we got the nth term test tells us 4, what would the nth term tell us? Diverges, right? Or a more likely scenario, what if we had this? Or I don't know if it's more likely, but another possible scenario, clearly diverges, right? But in this case, with this particular series, we got a big fat 0, which means the nth term tells us nothing. And maybe more specifically, move on to a different test, right? Because it didn't tell us anything. Okay, so it's nth term test is not going to help us. What are some other tests that we know? P-test, geometric series test, the integral test. We know 4 of them, right? And if you want to throw the harmonic series in there, like a unique one, that would be a 5th test, right? So is this geometric? How do you know it's not geometric? Yeah, the variable is not in the exponent. The variable is a base. Agreed. Okay, so we come down to like a p-series or harmonic series or an integral test. And the truth is, an integral test will definitely tell us what we need to know here, but it's not the easiest way. What's the easiest way? Say again? P-test would be a really good way. I think harmonic, the concept of a harmonic as well. We'll get into that stuff in a second. So I like the p-test idea. So let's identify it as a p-series. So it's a p-series, and in that p-series, p equals what? 1, yeah, because it's 1 over n to the first. So you could say then that 0 is less than or equal to p, which is less than 1. That's the relationship of our p in this one. And so if p is between, oops, I put my or equal to on the wrong spot there. Sorry. There we go. So in this case, because p is between 0 and 1, including 1, what's our conclusion? Diverges, yeah. So I hope that you will learn to like the p-series test, because it is pretty quick. Therefore, the series diverges. And the reasoning there would be the p-test. We didn't talk a whole lot about the harmonic series, but let's talk about it right now. If the harmonic series is 1 over an plus b, then the exponent on that n would be a 1, right? So what conclusion could you draw about all harmonic series? Diverge. They diverge every single time. And so an alternative answer to this question would be this. I'm not kidding about this. Check it out. You could just write this. That's supposed to be a therefore. I'm fine with that right there. It's harmonic, therefore it diverges. Done. Okay? So you could go through the pain of an integral test and get ln of infinity in there somewhere, right? And come up with your reasoning. That's going to take you like 5-6 lines of logic to get there. Or you can say, I know what that is. That's a harmonic series, and they always diverge. You're done. But you got to identify it as harmonic and say that it diverges, and that'll be good enough. Yeah, Sydney.
So you don't have to prove that you found that it was harmonic. You can just say it's a harmonic.
Yeah, I'm fine with you just recognizing it, because all harmonic series will be that 1 over an plus b, and man, you guys are obviously can see that. Once you see it enough times, you're going to be able to recognize that quickly. And if you can, I just want you to jump there. Unless you just want to do an integral test for whatever reason, which I would assume you would not. All right, let's take a look at our last one for the day. Maybe we'll finish this, maybe we won't, I don't know. Is to kind of help you guys build some logical progression of thought as to how we attack these, because it can be pretty darn intimidating when you see these out of context and you're just like, wow, what is that? And so let's build it from the start. Can you guys tell me, what will the nth term test tell me about this particular series? Yeah, you'll get 0, and so it tells you 0, right? It tells you nothing. Silent. Okay, so always at least consider that. Like I've told you before, in the past, I seem to forget about the nth term test at the worst possible moment, and that moment being when it would tell me actually something important, namely that the series diverges. It would be an easy way to prove that. Sometimes I forget that, so I'll always try to remind you of that. But in this case, yeah, the nth term test tells us nothing. Okay, so geometric series test. Is it a geometric series? Because there's no variable exponents, right? It's not geometric series. What do you think? Is this going to be a p-test?
Does the plus one make it not?
The plus one makes it not. Yikes. Yeah, because remember the p-test is very specific. It's not something like this or something sort of kind of like this. It's specifically 1 over n to the p. 1 over n to the p. So yeah, so it's not a p series. Is it harmonic though? Because maybe we could just like swing right on past this with a harmonic series concept. Why is it not harmonic? Squared. So at this point in the game, now later on there will be other alternatives to this, but at this point in the game, what are we forced to use? Got to use the integral test. Okay, so let's try that really quick. This will be good timing, I think. So I'm going to say, I'll just jump right in with the limit. Limit as b goes to infinity of the integral from 1 to b of 1 over n squared plus 1 dn. I don't know how hard this is going to push you. What? Good man. Awesome. Jared, you are doing awesome. Did you guys see that too? Yeah, so this is that arctan format. It has been a few months since we focused on that. Yeah, so limit as b goes to infinity of, and it's exactly arctan, right? There's no adjustments needed. So it'd be arctan of n, evaluated from 1 to b. So limit as b goes to infinity of arctan of b minus arctan of uno.
But what is, but like how many, but there's different answers.
Okay, you have to be a little more clear, but there's a different answer. I'm not sure what you mean.
Arctan of 1 could either be pi over 4 or whatever that is in the third quadrant.
Yeah, that's a great question. So arctan has a very, unless otherwise specified, arctan has a very specific domain, right? Arctan has to be between negative pi over 2 and pi over 2. It's got to be in the fourth or first. So we're restricted to those. Although your point is well taken, that's kind of the standard rule here. Okay, so as b goes to infinity, arctan heads where? Pi over 2. Good. We talked about that back in chapter 8. So it's pi over 2 minus, and then arctan of 1 is pi over 4. Yep. So you really honestly could stop right here. I mean, we know the answer is going to be pi over 4, but what's the most important part about this conclusion? Well, yeah, because when we do our integral here, we actually get an answer, don't we? That's not infinity. We actually get a real number answer. Say again?
But arctan isn't a continuous. Oh, but it's 1 over n squared plus 1.
On the domain from 1 to infinity, it is continuous. It's
Arctan?
yes.
No, because you have the absolute.
So there's two things I want to point out here. We're not talking about the continuity of arctan. We're talking about the continuity or lack of for that,
Yeah.
right? And so that just looks like this. So that's actually continuous for all x. And even arctan is continuous for all x. Arctan just looks like this. It does have horizontal asymptotes, so certainly its range is very restricted, but its domain is, whoops, what am I doing? Its domain is forever. Okay, so because we actually got an actual real number answer, what can we say about the series? It also converges, yeah. So here we would say something like, because 1 over n squared plus 1 is positive, continuous, and decreasing, and the integral from 1 to infinity of 1 over n squared plus 1 converges, we know that sigma from 1 to infinity of the same input also converges. And the name of what we just did is the integral test. Yes, ma'am.
Say on 1 to infinity.
Oh, yep. Did I not say that? I didn't say that. Thank you. Yeah, because we only care about the interval that we're actually talking about. Okay, so yes, Tess, question.
Oh, so do we, like, not have to go through and find out if it's positive, continuous, and decreasing before we start that?
So I think you should do that. I drew it out in a graph really quick. Maybe use a calculator, right? I think where you're going to be tested on that is simply, do you understand what the conditions are, right? Not necessarily how to prove them, but do you understand what the conditions are? So I think there'd be a number of ways to prove that, but I'm going to list them out here every time we use the integral test simply to reinforce that that's what the conditions are.
Okay.
And I think armed with a calculator, you can prove them in 2 seconds, right? And so I would think of it along those lines. Because you can't really, think of it like this. Just take one part of it. Continuity. How do you prove continuity for every single point on the interval 1 to infinity? How do you prove that? You simply can't, right? How do you prove positivity for every single point? Don't you have to look and say, hey, I looked at the graph,
Every point.
and it's always above the x-axis. Like that's kind of the level of proof that I would say. So yeah, awesome. Have a great weekend. See you guys on Monday.